Welcome to Supply Chain Design Week 8, Demand Forecasting. Demand forecasting has an important role in supply chain and operation management and therefore is vital for any business planning. If the estimates are too high, a company overproduces goods that cannot be sold. On one hand, this is unnecessary and moreover increases costs for resources such as raw materials, workforce, or storage space. On the other hand, underproduction can result in shortages and lost business opportunities and a potential loss of customers who could not be served. In supply chain, demand forecasting needs to be collaborated. When each stage in the supply chain makes its own separate forecast, these forecasts are often very different. The result is mismatch between supply and demand. On the contrary, when all stages of a supply chain work together to produce a collaborative forecast, it tends to be much more accurate. The resulting forecast accuracy enables supply chains to be both more responsive and more efficient in serving their customers. Leaders in many supply chains, from PC manufacturers to packaged goods retailers, have improved their ability to match supply and demand by moving toward collaborative forecasting. Two main methods in forecasting mostly used in supply chain and operations management: time series analysis, for instance, exponential smoothing, takes sales data from the past to estimate the new demand. Regression analysis can be applied to estimate the dependence between two factors. In addition, there are various other options for predicting future demand, such as simple probability, neural networks, and fuzzy logic, to name just a few. In addition to those, time series and regression-based forecasting, an expert estimate is a qualitative analysis tool that is drawn from historic demand and expert opinions on future development. Mostly, the method is used to forecast demand that was labeled hard to forecast. In this session, we apply two statistical methods, time series and causal methods, based on regression for forecasting and calculate the forecast, as well as measure forecast accuracy as forecast quality assessment. Demand information in supply chain and operation management is needed for production planning, revenue management, and inventory management. Production planning uses demand information to make capacity decisions at minimum final product stock level. Inventory management needs demand information to decide on how much and when to order. Revenue management uses demand information to predict consumer behavior at the micro market levels and optimize product availability and price to maximize revenue growth. The demand information is distributed across supply chain networks in order to produce production planning at each facility location. Similarly, demand information is used by process design and capacity planning to manage inventory at each facility location in order to minimize cycle stock without causing stock outs or back orders. About how much to produce and what price a product needs to be sold, revenue management receives information from both facility location and process design and capacity planning, and therefore it enables revenue management to calculate price sensitivity of demand. The forecast process consists of 6 steps. Define objectives, determine the time horizon, select the method of forecasting, gather data, perform the forecasting, and validate and control the result. In our example on this slide, we want to forecast the number of handouts should be printed for the next lecture. The next step is to define the horizon. We should keep in mind that a longer term forecast is usually has higher level of accuracy than a shorter term forecast. The next step is to determine what forecast method to be selected. In this case, the time horizon is a week. For such short-term issues, time series analysis is a preferred method. Based on the attendance of students from the last lectures, exponential smoothing can be performed to predict demand. For longer-term forecast, where the data is not function of time but as a correlation between an independent variable and a dependent variable, causal forecast is preferred, and an example of the method is regression. The next step is to control the forecast by monitoring the accuracy of the forecast method by measuring its errors. Based on the previous example, both methods, time series and regressions, are categorized into quantitative method. The method relies on historical data, such as demand numbers or turnovers. This works well as long as a company has reliable data which is available for the required forecasting. But how if the situation is vague and little data exists? We can use qualitative methods. Qualitative methods are used when such situations have a long-term nature or decisions are to be taken about new technology or products. The forecasting for such cases involve intuition and experience. In this case, they have to rely on expert view and customer opinions. This expert type of forecasting is normally based on professional knowledge and experience. A company uses this input from different experts to develop forecasting for the next period. The problem with the expert method is that they are based on opinions, experiences, and knowledge of human beings. There are also different methods for qualitative forecasting. For instance, sales estimation, where a company asks their sales expert about the latest turnover figures and aggregate the data for the overall turnover, using the data to develop a forecast. Other qualitative methods is the customer survey. Customer survey is good to use when a company launches a new product when there are no historical data or expert experience. A company can ask their customers directly what they are thinking of the new product and try to develop a forecasting for the product launch. The third method is the basic idea of qualitative forecasting, expert view. A company asks proven experts about new technology or their experiences with related products in the past. These experts are normally working in different departments of the same company. The best known qualitative forecasting method is the Delphi method. It is an extension of the expert view, and the feature is a structured multiple expert survey using specialists from different companies and institutions. The Delphi method runs into 2 or more rounds. A moderator develops a questionnaire and all the experts reply anonymously. After the first round, the moderator creates a new questionnaire based on the information he got. Answers to the first round are published to all other experts so everybody can rethink their view. Next, they fill out the new questionnaire and so on until it leads to a consensus. The next method is causal forecast, and we take an example from linear regression. This slide shows 2 different types of regression in causal forecast, linear and non-linear regressions. For linear trend, the demand can be found using the least squares method. The correlation between demand Y for product and a known factor X is linear, where every time variable X changes by 1 unit, that affects to the change of the demand at rate B plus an intercept A, and therefore intercept A signifies the least value of the demand Y or the lower bound of the demand. In addition to linear regressions, non-linear regressions is more complicated but also more realistic. An example of it is shown in our slide that takes a form of logarithmic regressions. However, the formulations of non-linear regressions are more than that, can be exponential or polynomial regression. Solution methods of polynomial regression are mostly heuristic. Machine learning algorithms, for instance, such as artificial neural networks or ANN, support vector regression or SVR, or random forest regressions can be used to forecast demand when the formulation is polynomial. In addition to the previous linear regression method, in this slide we go into time series analysis. There are different demand patterns that can be analyzed by using time series. Time series is based on historical sales data. Sets of evenly spaced numerical data can be obtained by observing response variables at regular time periods. This method actually forecasts on the basis of the past values and assumes that factors influencing past and present will continue to influence in the future. There are different methods to forecast demand depending on the temporal progress of demand. We can see from figures in our slide, if there is constant demand for a product, we can use the moving average or simple exponential smoothing. For products with a demand which is based on trends, we can use regression analysis or double exponential smoothing. Products with seasonal demand can be forecast using triple exponential smoothing. Simple or single exponential smoothing uses a weighted moving average with exponentially decreasing weights due to the existing of smoothing constant as a level component. Therefore, it is appropriate to steady demand. Holt's trend-corrected double exponential smoothing is usually more reliable for handling data that shows trends. Compared to the single procedure, double exponential smoothing employs a level component and a trend component at each period. double exponential smoothing using two weights, also called smoothing parameters, to update the components at each period. Triple exponential smoothing, also called multiplicative Holt winters, is usually more reliable for parabolic trends or data that shows trends and seasonality. Triple exponential smoothing employs a level component, a seasonality component, and a trend component at each period. Triple exponential smoothing uses three weights, also called smoothing parameters, to update the components at each period. This slide shows how to measure forecast quality. There are three metrics to be introduced in this session. First, mean absolute deviation. Second, mean squared error. And third, mean absolute percentage error. For first, a metric that is mean absolute deviation, it measures the absolute deviation epsilon of forecast and actual data over t periods according to the formula of MAD in our slides. And the second, mean squared error, measures the quadratic deviation of forecast and actual data according to formula for MSE in our slide. The difference between MAD and MSE lies on the square sign. For MAP, it measures the percentile deviation of forecast and actual data according to the formula for MAP in our slides. Each of those metrics has its own advantages and disadvantages, as shown in the next slide. The absolute deviations, or epsilon, of forecast are measured at each period across forecast time window. The practical problem with the MAD measure is that it expresses the absolute values and is therefore quantity dependent. This makes it difficult to apply MAD for comparison of forecasts for different products which have different magnitude of average demand. For instance, deviation of 100 is relatively low for average demand of 1 million, but high for average demand of 1,000. MSE is frequently used because of its good theoretical properties, but may be negatively affected by so-called outliers or freak values. An outlier is a data point that falls outside of the expected range of the data. For instance, it is an unusually large or small data point. If we ignore outliers in our data, there is a danger that they can have a significant adverse impact on our forecast. If we include them, the quadratic value of those outliers will change the results of our forecast significantly. Therefore, MAP is intuitively good and understandable and can be used for comparison of different forecasts where MAD or MSE values differ. In the current slides, this slide gives an example of using linear regression of demand forecast. There are 6 weeks demand data. The second column of the upper table shows the amount of transaction by customers, and the last column of the table shows the amount of sales by the customer from week 1 to 6. We copy all information from the upper table and move and paste them to lower table. The square values of the amount of transaction by customers are shown in the third column of the lower table. multiplication of the amount of transaction by customers and the amount of sales by the customers are shown in the last column of the lower table. The end row of the lower table shows the sum of all values in each column. Next, we start building the regression model for our problem example. This slide shows how to compute equation coefficients A and B. For calculating B, we need information from the lower table of the previous slide. We need to input the time windows, that is equal to 6, and then multiply the time window by the sum of the last columns, minus sum of the second multiplied by sum of the third column. As a denominator, to input the time window that is equal to 6, multiply by the sum of the fourth column, minus the square value of the sum of the first column. Dividing the numerator by denominator, we get B. Okay, we can repeat. For calculating B, we need information for the lower table. For instance, the time window. Here we have 6. And then sum of the last column, that is here 185, 956. And then we have also sum of the second multiplied by the sum of the third of the second multiplied by sum of the third, right? Divided by, this is the time window, 6 periods, times the fourth column. Here, sum of the fourth column, 2884. Okay? And then minus the sum of the second column. Here, 330. And then we have 7.263 as a value for B. And we can also calculate A with the same way by following equation in our slide as follow here. By referring to our previous table, the lower table. And we found A equal to 103.868. And then we can put those two values into our regression equation. This is A, this is B. And we finally get our regression model for the problem in our slide. Next, we would like to calculate the model accuracy. The current slide copies the first 3 columns from the upper table of slide 10. So this is the first 3 columns we get from here. The first 3 columns we copy these 3 columns and put into this table, right? And also the fourth column of this current table, yxn, is obtained by employing this model by changing x with value of 1, 2, 6, and we have the following values, right? And what about the error? The error is the discrepancies between yxn and the actual sales, and we have these values, and we square this error, and we have square error here in this last column. And therefore, mean square error is the value of the total of mean square of square error divided by the number of week equal to 6, and we found 872.462.